one won't be, here it is. Okay. That'll be the quiet, like those silent movies, you know, that everyone grew up watching, right? I could definitely get rid of the red. Anyways, what were some of the main points we talked about? Translational to rotational, making sure I have, if it is sum of torques, I've got to make sure everything is in torque. So that means first defining my spring force. That's a difference between two. This is all based on the small angle approximation. Just being careful of what is my perpendicular distance? What's my moment arm? So force times distance equals torque. Okay, next up, rotational. We did this problem. This was week 2, day 1, or week 1, day 2. One of those. If it's a purely rotational problem, I know sometimes these can be a little bit difficult because it's more three-dimensional. So what I would say is just pick a side, like what direction you're going to look from. That's an important part. So for example, and I will post these slides. So if I'm looking from this direction, I've got J1, I've got J2. So that means theta 1 is going this way, theta 2 is going this way. And then I can put my different torques in. And if you bring two pencils, you know, it might help with like, okay, what happens if I turn this one? What happens? Like if I say theta 1 is greater than theta 2, because we don't know, so we're just going to pick one and roll with it through our definitions, through our free body diagram. If I'm saying theta 1 is greater than theta 2, which way is TK going to act on J1? If I'm saying theta 1 greater than theta 2, which way is TK going to act on J1? Counterclockwise, yes. And so what does that mean for J2? Which direction should that be? Clockwise, always. Equal and opposite for a spring. So again, you can pick the direction, it's fine. Just make sure they're equal and opposite, and then your definition should match. Now, we can always check at the end if I've got negatives in my output equation. On the output side of the equation, that's a sign that maybe I messed something up. It should always be positive, it should be stable. Which way should TB, the friction torque, be acting on J1? Counterclockwise? But all the other torques are counterclockwise. Wouldn't it be fighting those torques? No, it wouldn't. Well, it opposes a positive motion. You're absolutely right. Don't look at the torques. I don't care which direction those are. I'm looking at this. If it moves positively, I'm going to have friction oppose it. Same thing for the other one. So do not look at the other torques to set this up. It's just our equation is going to be, hey, for any positive velocity, which is clockwise, I should have a friction that's opposing it. And then if it is negative, well, that makes the definition negative, so I'll flip the sign automatically for you. So we should always look at that direction. Anytime I've got a friction between an object and the wall, we want to go against the positive direction of motion. Questions? We're not going to do this problem. We did this problem. Again, I think it was week 1, day 2, possibly. So that's a good thing. Besides maybe going back to some of the homework problems, you can definitely go back through some of the slides. We did a lot of different example problems, so you can try it. go through and then, you know, scroll through the slides and see if your thought process was correct. That's one way to check yourself. Another thing we talked about was gear trains. So this was like part of lab 1 with the cars, the pullback cars. Let's see, what to know about this. I always like to draw it. So if I've got like, this is my R1, this is R2, there's a contact force here. And so let's say this thing is spinning, this is my omega 1. That's going to make this one spin this way. So omega 1, omega 2. Now this gear is going to feel a contact force pushing back on it. Like gear 1 is going to try to move, but there's another gear in the way, which is R2. R2 feels that same contact force, equal and opposite, pushing on it. So the torque here, the contact torque is just equal to the force times the radius. So both of them they're not equal torques. The higher the radius, the higher the torque. And we do have, for a gear, the gear ratio is equal to R2 over R1. This is the same as T2 over T1. That's really that torque that if I'm going from one to the other is, you know, if I'm stepping down my radius, so R2 is less than R1, then therefore this torque is going to be lower than that one. But torque and speed are they're inversely related. So my omega 1 is going to be less than my omega 2. And you can go down the line with this. This is also the same relationship, not just of speed, but of angle. So I can relate it to theta. I can also relate it to acceleration. So those are all directly related. I can look, you know, these still have all the same, at that mesh point, the same velocity. So omega is really just velocity times radius. Everything is just really based on the radii of those two gears. Okay, so that was most of your experience. Lab 1, just kind of going from one gear to the next, seeing how torque kind of changes, as well as theta. Questions? Okay, that was mechanical. We talked about some of the electrical laws. KVL, KCL, those are like your starting points in your definitions. On your diagrams, one thing that I would really recommend, now you're going to use full body, but you do have the option of, you know, doing all the KVL, KCL, just keeping the circuit as is. You also have the option of impedance. So maybe you take this and you combine things. So draw a new simplified schematic. You're going to make a drawing either way. What I would say is don't forget to draw the currents on here. So like in this case, I have an input current that's going to split to two different currents. So maybe I call this one, you know, inductor current, call this one capacitor current. Anytime I've got a node, it's going to split. So I would create a KCL right here, where IN is equal to the sum of those two. How many KVLs can we do? How many loops, closed loops, do we have? We have two closed loops. So how many KVLs can we do? One. Why is that? I can only really do, if this is loop 1 and this is loop 2, I can't do a KVL1. Why not? Because I have a current source. I don't actually know what the input is, but I could do a KVL2, which will basically tell me that the voltage, because current always splits to give you equal voltages, this voltage is equal, capacitor voltage equal to the sum of R and L voltages. Right, so far. So there's still a lot of time left. 7. You said 7 people. What? Oh, yeah, you said 3, right? Oh, 5. Okay, questions? And again, you can do either option as far as impedance, whatever kind of makes sense to you. But make sure you go through the steps, draw it out, just write down all the, that's Bobody, the point of Bobody for each of these problems is to write out all the stuff, and then you can try to take that information and get to the final equation. It also helps me see your thought process. So even if you don't end up using it, maybe you should have used something, but you had it written down. So there are partial points. I'm not going all or nothing on this. Anyone have all or nothing before? No? Okay. Oh, yeah? Okay. Op-amp. So there's some laws on the equation sheet, and the two ones that you really should know are first, so this is on the equation sheet, which is provided with the test, that there is first that EA minus EB equals 0. So the two voltages at the terminals, the negative and the positive terminal of the op-amp, the difference of the voltage is 0. And if this is grounded, which it normally is, then what that means for us is if grounded, then both of these are equal to 0, which means at this point here, the voltage is equal to 0. And that can really help. By knowing this, I know that, hey, I have input voltage, and then I go across the resistor, and I'm back to 0. So you have that relationship. It's like a simplified KVL. I don't have to do the whole loop, just going from 0 volts to 0 volts. Same thing on the right-hand side. I'm going from 0 volts, then I drop across the resistor, and I drop E out. So there's a relationship there as well. Drop, drop. The second law, which is also really helpful, is that the current entering the op-amp is equal to 0. It's negligible. It's not drawing any current. It has a very high impedance. So if there's no current going through, that means that then I1, in this case, is equal to I2. So those two are equal. So those are the main things. Then from there, you can do KVL. You don't need to do KCL anymore. We're actually not really worried about the gain. So always with these ones, we're looking at a transfer function of output voltage over input voltage. Is that relationship? Questions? Oh, Jared, I thought you had a question. You got a job interview? Oh man, crackdowns. People have to go back to work 5 days a week. I got a friend, he just got a job at Maserati and just got a job there, and they were like making everyone show up back at work. And he signed the job that it was remote. Anyways, kind of rough. Okay, DC motor. Remember, a motor has an armature. It's got a big coil of wire around it. That's what this represents right here. So if I plug in the battery to the drill, that gives me power. I have a resistance of that big coil of wire, more resistance. I have inductance because it is a coil. And then what is this thing right here? E sub B. Well, this is called the back EMF voltage. And this is equal to, there's a constant, K sub B, that's the back EMF constant, multiplied by the speed of the rotor. So basically, the faster this is spinning, the more voltage it's creating because it's in a magnetic field. And that voltage is fighting against the input voltage. So therefore, the current is going to slow down a little bit the faster that it's spinning. This also, the same KB relates to the motor torque. So the motor torque is equal to that same constant multiplied by the current. So that is the back EMF constant. That's what ties the two together. These are on the equation sheet for a motor underneath the electrical section. You remember seeing that? Okay. Cool. That's mostly what you need to know. Now you're going to still, for any kind of hybrid system where you got, either it's electrical, mechanical, or whatever, you're going to do, okay, I'm going to look at this system. I'm going to make an equation for this one. I'm going to look at this system, make that equation. Now these definitions tie them into each other. So there's got to be some kind of crossover. Okay, so that was, I think, what we mostly did for circuits. Hydraulic, we just covered last week. You just did homework 3. So there was one problem in there that was a little bit different than what we did in class. Basically, like on the equation, I'm always going to start on the equation sheet. We have an equation where we have Cp dot is equal to the sum of Q, which is volumetric flow rate coming in, minus the sum of volumetric flow rate going out. So if I have one input, one output, great. But that's all based on Q out right here is based on the resistance of this valve, right? If I open the valve, and you've turned on the spigot before, right? If I only turn it a little bit, I have a pretty high resistance. I'm not going to get much of a flow. But if I open it all the way, there's less resistance. And so that Q out is equal to the delta P over R if it is laminar, and laminar is linear. So in this case, delta P, I'm going from high pressure, which is the pressure of the base, minus the atmospheric pressure all over that. And we can change it to height. You know how to change pressure to height? It's a tank. Yeah, pressure is equal to rho GH plus P atmosphere. So rho GH is gauge pressure. Absolute pressure is going to be adding the atmospheric pressure. And that's on the equation sheet too. So you can always just write these down, at least these, and then try to figure out, okay, for any flow that goes across a resistor, I'm going to use this kind of equation. And then from there, we try to set up our equation. And it should, just like all these problems, if I get a negative on the output side, I probably messed up something. Maybe it was my definition was flipped. Maybe my algebra was just wrong. So that's something I've also seen in the homework. Just be careful with that. Now, there's for sure mechanical and electrical on the test. There could be hydraulic, there could be thermal. Obviously, most of this class we cover mechanical, electrical. So if you don't feel good about one of those two, that's something you want to brush up in the next 2 days. That's for sure on the test. This could be something like this could be on the test, or like the thermal problems you saw in the homework as well, which I'll cover. Any questions? Hydraulic wise, temperature wise, we have a very similar looking equation. It's CT dot, but instead of just having a sum of Qn, which is heat flows, minus sum of output heat flows. We also have, if there is fluid coming in with a temperature or fluid leaving with a temperature, we want to include that. So if my problem is just heat exchange, like the cup from the homework, then I can forget about the fluid. I can just get rid of that. I can just look at the Q's. But in the case of this problem here, shown on the page, there was fluid coming in with a temperature, then it was exiting with a different temperature. We had different heat transferring between the two because it is a heat exchanger. And so that was done last week, so you can check it. And yeah, basically you just want to start here. You want to put your diagram together, show Q's. What I noticed was that for hydraulic and thermal, make sure if I've got a boundary or I have a resistor between two different parts, hydraulic or thermal, for every resistor, there should be a flow across it. If it's, uppercase Q for hydraulic, lowercase q for thermal. Any kind of resistant boundary, there should be heat going across it from one body to the next body. Does that make sense? Yeah. Are you ready to do a problem? Practice? All right. This is nope. It never really wants to update this doesn't even have that much stuff on it. I think it's literally just. All right. Well, this is your problem. We're getting closer. I want you to find. Oh, there it is. We want to find the transfer function theta, the motion of this, over the input, which is xt, which is the displacement. It's shown at equilibrium. Now, this is like the more realistic depiction of what this is. So we've got a rocker arm. This is our camshaft. We have a follower. So it's going to be always kind of pushing this. We have a return spring. And this is the simplified model. So we are creating a transfer function for the system. So this is a really good test prep. That's why we're doing it. So I want you to follow Bobati. I want you to think through it. If you have questions, you can definitely ask me. And then eventually we'll go through it kind of at different parts as we go forward. So let's start Jeopardy. Yeah, you should have. Yeah. Oh, that was just about. Oh, yeah. Yeah. Human, human system. Hydraulic, thermal, everything. Okay, so as the problem says, x sub c, the cam movement, that's the input. So we have a displacement that's an input, not a force. That goes through the spring, and then turn the hand or the rocker arm. So, what is the order of this system? It is second order. All I've got is one body. The rocker arm is the only body we're worried about. So it's going to have a theta double dot. We're going to do a sum of torques for this problem. So you want to draw your body diagram. And we know what our input and output is. After that, it's just trying to define it and go from there. So if you have questions, let me know. Um, it is. This is what I'll say for the body diagrams. If you have anything that's round like this is not a force. That's a torque. Anything that's rounded. But if you have something that's a force a distance away, you can label that as a force. But anything round should be a torque. We're going to do sum of torques. Yes. Yes. Hey, you want to see one? This is good. Whoever does better passes. Very helpful. Well, that's obvious. You don't want to be stuck having a two report, you know? Yeah. Yeah, what? Sure, it is. That background mentioned days, that's the body day. Still working. I've always flirted with the idea of just putting this problem directly on these. This one should. You guys seem to have a fun time with it. There are. I should? Yeah. 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 Huh? No, don't worry. We're still trying to find, again, our goal is to find theta over displacement x. But we just said, we're looking for 1 second order equation where we're going to have a theta double dot. And when it comes to inputs, outputs, that's also pretty easy. It's just going to be output, input is the displacement, output is theta. Now we should have either. We should have, in total, 3 torques acting on our body. 3 different torques, 2 of them related to the springs, 1 of them related to friction. So I'm not going to fill mine in just yet, but from those 3 torques, now you want to define them, because we do have, like we just started class with, although half of you missed it, translational to rotation. So I have some translational spring, but everything should be in terms of the end of the theta. So how do we relate these to theta? Yeah, I just put up two different types of free body diagrams. Some of you may be more inclined to use one or the other. I kind of like this one, just knowing that these are two linear forces because I have translational springs. So it's going to be a force times a distance to give me that torque. Now, it doesn't matter which direction you have FK1. Both ends can move. So you can say it's either in compression or tension. I chose compression where XC, the input, is larger than L1 theta. But you can also draw it this way. So we should have those three torques. Now the trouble is, what some of you are maybe figuring out is like, okay, how do I define FK1? How do I define FK2? TB is pretty easy. And so what I would say is, for if this is L1, this is theta, we're trying to find like the distance here. So that spring for FK1 is going to see that distance right there. You want to figure out what that distance is, because that's going to inform your spring. So just drawing stuff out, giving yourself time to work with the equations. Both of these springs, see, it's related to theta, but we want to figure out what that distance is. So that's using the small angle approximation. If you got any questions, let me know. Or if any of you, my subscribers, have any questions, just drop me a comment. I'm not gonna check it. I'm sorry. Blowing up though. Yeah, like I gotta make the end page and everything. Yeah, and put some music to it. Shoot, I can put my own music. No copyright needed. amazing. You want this problem on the test? This exact one? You don't want this one. Exactly the same. Except XC is changed to XB. What if I flipped it upside down and backwards? Still the same equation. You want that? It's a good trick. Yeah? Is it right? Uh Yep, that's true. Okay. What's X not? X0? Oh. Oh, okay. But change this to X1 because just to match what I've got on the screen, because there is going to be a difference. XC is my input. X1, so K1 really is looking at the difference between XC on the bottom and then X1, which I kind of put on the slide. But X1 is really related to theta. So now you can change X1 to be theta. X1 is related to theta. I don't want X1 or X2 in my final equation. I'm just putting there as kind of placeholders because I know my spring sees that vertical movement, but that vertical motion is related to theta. There's some. Oh, okay. Yeah, no. It seems like the setup is
It's kind of like, I think I messed up my page.
now this should have a K in front of it too.
Yeah.
But then all these thetas, when you add them, they're all gonna add to the other side. All right, I'll give you a couple more minutes to try to solve it, and then we'll take a break. We'll finish it and take a break. Yeah. Mm-hmm. So my spring force, just to give you a real FK1 is K delta X. I do have a delta. I have XC. I'm saying that XC is greater than L1 theta. Because X1 is equal to L1 times sine theta. If I'm looking at this right triangle, L1 sine theta gives me X1. Sine goes away. I'm just left with L1 theta. That's how we linearize it. So therefore, my spring force in compression is K times XC minus L1 theta. What? Maybe? And then for K2, you've got to do something similar. Now, K2 doesn't actually have a delta because it's tied to the ground. So it's really just going to be looking at theta, making sure we get a, eventually, we should change everything to a torque to do sum of torques. What's going to happen? Okay. So I'm just gonna keep going. I'm gonna start writing my definitions. So damping, put the friction that's between the object and the housing or whatever. There's no delta, that's just going to be B times theta dot. But my two torques should be translational forces times the distance, which technically is L1 cosine theta, but cosine theta becomes 1 for small angles. Great, here's all my definitions. Again, translational spring, distance away. So first, I know it's sum of torques. I know it's rotational theta. So torque is equal to force times distance. Okay, I can get all those. My friction's pretty easy. It's just going to be B theta dot. But the hard part is these force definitions. So this spring, FK1, is between 2 points that move, XC, and what I can say is X1. That's the vertical displacement that I drew on this slide. Down at the bottom, X1 is my distance, X2 as well. They're related to theta, so I can replace X1 with L1 sine theta or L1 theta, and then I can again use my torque, so I just multiply that by another L1. FK2 doesn't have a delta. It is between the object and a wall. So therefore, it's just looking at what I could say is X2, that vertical displacement. X2 is a small part of that triangle. So I can say it's L2 sine theta, or simplified to L2 theta, and therefore my torque looks like that. Again, anytime I've got a theta multiplied by this, which is in radians, the radians go away. So K is newtons per meter. If I have meters squared, this becomes Newton meters. So that's another way I can kind of check. Yes, it's torque. It should be Newton meters. Now, the last part should be the easiest. I've got everything. I've got my diagram. I've got my definitions. Now I just need to put it together, do a little bit of algebra, and get all the same output variables to one side. But questions up to this point? Want me to go back and explain something? Okay, because on the next slide, I'm just going to take the sum of torques. I'm going to use my diagram to set this up. So sum of torques equals J theta double dot. I've got a positive TK1, negative TK2, and a negative TB. So this is K1 L1 times the input minus L1 theta minus K2 L2 squared theta minus B theta dot. And I can see that all of my thetas are negative. That's a good sign. So we're going to bring it over to the other side, all of the thetas, going from highest order to lowest order derivative. And I can even combine these. I get K1 L1 squared plus K2 L2 squared is equal to K1 L1 times my input XC. And lastly, we wanted a transfer function. This is nice. It's linear, single input, single output. So if I wanted to get output theta over input, I change all the dots to S's, and I get K1 L1 numerator over JS squared plus BS plus K1 L1 squared plus K2 L2 squared. That is my second order transfer function. We knew it was going to be second order. It is stable. That's another thing. So the bottom of this is all positive. That's a good sign. And it's got all the components. It's got all the K's. It's got the B, J. All of those are on in my transfer function. Questions? I'm going to leave this up here. If you have questions in the next 5 minutes, let's talk. So let's take 5, and then after that, we'll do a circuit problem. So it's 8:25, 8:30. We'll do a circuit problem, and then if you have any other following questions, or if you have any questions right now, I can try to answer outside of this problem. Huh? Oh, gotcha. Yeah, that'll be tough. That'll be tough. You got it. Hmm. Hmm. Which free body diagram do you like better? Yeah. Well, because you could say TK1 is FK1 because it is a linear spring. So it's going to be FK1 times the distance L1. And that's what our definition is. TK1 is equal to FK1 times L1. So if I just draw the circle as my free body diagram, sure, I go, yeah, I'm going to have a TK1, but really if I break it down, it's going to be a vertical force times a horizontal moment. That's why I kind of like drawing it as a bar, just to show it's technically a force times the distance. Huh? Okay. Okay. Double half. The math won't add up. Double the 50. 50. We're going to be missing 25 points. Where does those come from? Extra participation. No, coming to class on time gives you extra participation. Like if you're here right when class starts. You're right, there wasn't. Next year I can change the class. Be good. I'm having students tell me I need to do more Taylor series in this class. Can you imagine that? They want Taylor series. You guys like Taylor series? Yes. Yes. We do end up going there, yeah. Square root at -1. Oh, the square root of I. We should do that. You're right. It's good. Let's see, it's 8:30. Welcome back. This is a random picture I took from Chad. And I want you to solve for E out over IN. I crossed out some things because they had some like values. We don't do numbers yet. That comes next, maybe next or the week after. We'll start doing some numbers eventually. But right now I want you to solve the transfer function, E out over I in. And you can use whatever method. You're still going to use Bobati. You're still going to, do the order, diagram, definitions, and then whichever method you want. Going through all the different loops or using impedance method, whichever way makes more sense to you, or you can try to do both. You got time. Huh? No? Oh, good. Brown. I mean, it's all of it. Yeah, you know. Oh, Dom's music great. Really great. Doc Brown. Anyone choosing impedance or the traditional loop method? Maybe it's kind of mixed. What is the order of the transfer function we're trying to find? Second. So I have a one inductor, one capacitor, so it's going to be second order. Each one gives us a first order equation. Obviously, we've got inputs and outputs. Now, the input is going to be I, and it's a current source. The output, we could look at inductor current, capacitor voltage, but ultimately, we're going to get to a transfer function where we've got E out over I in. So that's what the problem is asking. Body diagram. I've got my diagram down there. It's not the prettiest because I had to scratch some stuff out, but I do have all my different currents. Now, what you could do if you want to do impedance, one thing we could do is simplify this a little bit. Where I could create a Z equivalent. Here's R1. Oh, that should be an inductor. I can draw as that. So I still have different currents. This would be my inductor current. This would be my, I don't know, maybe I'll call it I sub Z. But my output is E out. You don't have to do it this way. This is just one way I can group up that R2 and that capacitor together. So I can make a system like this. Now I can't really simplify it a whole lot more than that. We're still going to have to use some kind of KCL, KVL-ish to be able to solve this. But either of these works. These kind of drawings. So now it's going to your definition. So either I'm using impedance. So for inductor, it's L times S. Capacitor is 1 over CS. Those are the impedances that we can use. Resistor is just R. Or if you don't want to go that route, okay, let's look at the loops. Let's do some KVLs. Let's do some KCL. Let's get all these equations going and the equations on the equation sheet so we can then solve. So I'm going to give you some more time to work on this. If you have questions, if you want me to check something, go ahead. I can check it, see if you're on the right track. Got a question. We're looking for E out over I in. E out over I in. So that's what we want to find. I just if I'm looking at impedance, I can look at it as all basically resistance. Every element has resistance. So that's why I just changed it to like CL. That's the impedance of the inductor. So well, because the capacitor and R2 are in parallel, I can just combine those. So I can just look at the combination of those and then just one current, like the combination of those two currents going through. Hmm. Just has a raise their hand, so I know who's going this route with the KVLs, KCLs. Who's going this route? And more of you this way. Okay, fine. Either way works. We're still gonna need to use KVL, KCL to solve this. If you want me to check something, I definitely can. We should end up with a second order transfer function. Stump. We do it together. Second order. Trying to find it. Let's do it together. Yeah, I'll do it with the impedance method. Just because most of you are. We should be able to find it both ways. But let's dive in. First off, we all start with the same way. Now, for impedance, I did simplify this circuit a little bit just because I've got R2, I've got capacitor, and E out is going to be equal to that. I can combine both of those impedances together for Z equivalent. So the first thing that I did after writing the basic definitions was to find Z equivalent. So because they're in parallel, I add up the reciprocals and make sure I get a common denominator here, and then make sure that I flip it because it is reciprocal. So 1 over Z equivalent, I flip it to Z equivalent. That is my Z equivalent right there. So I'm going to go to the next slide and try to put this together. Our goal is to get output voltage over input voltage. Actually, real quick, what is E out equal to? E out is equal to, based on this, what is E out equal to? Yes, Z equivalent times, I called it I sub Z. So it's not the full IN. What is IN equal to? IN, this is my KCL, is equal to inductor current plus the current going through the rest of it. So we're going to have to use that definition to be able to set this up and eventually maybe cross out some IL. So we got a lot of work ahead of us. Some of you were trying to work through it, trying to figure it out. We'll go through it now together. But before I turn the page, any questions about these things? Again, you can solve it either way. It's just writing down all the definitions and then trying to simplify from there. So let's start with a few things that we know. Here's IN. Here's the equivalent. Here's R1. This is IZ. So there's my graphic right there. E out is equal to Z equivalent times the current I sub z, where z equivalent is equal to R2 over R2 CS plus 1 and IN is equal to IL plus IZ. So I'm close. Now what I can do is I can substitute IZ in here. So E out is equal to R2 over R2 CS plus 1 multiplied by, we've got IN minus IL. Okay, now I need to get rid of that IL. Now, should I just cross it out? Be done with it? And then just, this is good? This is my oh wait, no, that's first order. And then there's gonna be no L in it. That's not gonna work. All right, what is IL equal to? What is IL equal to? And this is where we probably need another KVL. So I have the current splitting here. IL, we could say, is basically the voltage across the inductor divided by its impedance, but that might be a little bit confusing. Let's look at this loop. I'll call it loop 2. So KVL of loop 2. If I go around, there is ER1. So let's say I just start at the node right here. I have a drop here. I have a drop here. And then I have the voltage across the inductor. This gets me back to 0. So I can say that the voltage across the inductor is equal to ER1 plus EZ equivalent. This is the hard thing. Like if I didn't have that resistor, this is a much easier problem. Because I can really just combine all of these. That's my E out. We have one transfer function, no problem. Problem is that resistor right there. And so really, because I don't have an IL and I don't really know what that voltage is, I set up this KVL to say, okay, current is going to split to give me equal voltages. So the voltage across the inductor is equal to the combined voltage of the resistor and Z equivalent. And so we can set this up a little bit different. So this is, we know that voltage, E is equal to Z times current. That's just like Ohm's law. And so I can say this is the impedance of the inductor multiplied by the current going through the inductor. This is equal to R1 times that current IZ plus Z equivalent times the current IZ. So basically we can say Z equivalent plus R1 times I. And now I can solve for IL. So I don't know if you see where this is kind of going. But I can get IL is equal to Z equivalent plus R1 over the impedance of the inductor times IZ. So, we're closer. It might not look extremely great. Let's go over what this means. IL is equal to Z equivalent, which is R2 over R2 CS plus 1 plus R1 all over LS. That's the impedance of the inductor. So we can rewrite this as R1 R2 CS plus this plus R1 plus R2 all over. This becomes R2 CLS squared plus LS. Okay. So, and you can take your time with this, right? I'm just kind of going a little bit faster just so we can get to the finished product. But to get this, first forget about the LS. I'm going to take R1 times that denominator to give it a common denominator. So that's the R1 R2 CS plus R1. I add that to R2. Now I've got a common denominator. Then I divide that by LS. So that basically I can multiply to the bottom. And this gives me my second order. So we're a little bit closer. Maybe you see, once I have this, now I have a definition for IL. Well, this is multiplied by IZ. So I've got all of this. I can now plug that in. And IZ is pretty easy because that's just going to be E out over Z equivalent if I go all the way back here. And so what I could say is this is equal to the R1 R2 CS plus R1 plus R2 over R2 CLS squared plus LS multiplied by, I can just say this is E out over Z equivalent. And so some of these things will eventually cancel. It's going to be a lot of writing. So some problems are a little bit more straightforward than others. Really, this resistor R1 kind of gets in the way of making a nice, easy thing. So I've got to take this, and I don't know if impedance is a faster method on this problem. Sometimes, it can be faster in some ways. If this gets really confusing, which it probably is, maybe I go to the other method, where I'm just going to look at all the different loops and see if I can combine it through those methods, the loop analysis. So both of those are fine options. If you get really stuck, try the other option. Just kind of back up. Let me start with clean definitions and kind of work from there. Is this all way over your head, or is you somewhat following? Somewhat following? I don't know what the thumbs up was for. Maybe? Okay, I will post these slides. Now, my goal is to, I'm going to plug this in here. And we're going to see what comes out of it. So let's see. I've got this E out. Let me start with this equation right here. So this will be equation 1. I'm going to take that to the next side. So this is E out, equation 1. E out is equal to R2 over R2 CS plus 1 times IN minus IL. Okay, so if I go back here, this is now my IL. So I'm going to take this big thing and we're going to expand it out. So we got the R1, R2 CS plus R1 plus R2, all divided by R2 CLS squared plus LS. This is multiplied by, maybe I'll put brackets. This is multiplied by E out over Z equivalent. So what I can do with this Z equivalent, what we can do is if I rearrange this E out over Z equivalent, so if I divide both sides, that gives me R2 CS plus 1 over R2. And so I can put that here, E out, R2 CS plus 1 over R2. That's pretty complicated. It is. But we can do some algebra and do some cancellation. So, for example, this is going to have some cancellation here. We're going to see, let's just go for it. E out equals, I'm just going to keep this as is. We have IN. This is going to become what do I want? R1, R2 CS plus R1 plus R2. This just becomes LS times R2. So we had a little bit of cancellation. There is an R2 CS plus 1 here. So those cancel. There's a cancellation that's part of that. Because I could just say this is R2 CS plus 1 times LS. So that cancels out, so I'm left with an LS. And so we can combine these. I get an R2 times LS, and that's going on right here. We're almost there. I've got E out. So now I don't have anything else. I don't have any other currents. I don't have any other voltages, nothing like that. That's what I'm looking for. I'm trying to get to this point. So now that we're here, I can get all the E outs to one side. This is going to be E out times, I can have a 1 right here, plus, this is going to be R1, R2, CS plus R1 plus R2, all over, let's see, the R2s cancel out. I get R2 CS plus 1 times LS. That's my E outside, and then on this side I've got R2 over R2 CS plus 1 times IN. And So this becomes E out. So to add that 1, I get R1, R2, CS plus R1 plus R2 plus R2 CS plus 1 times LS over R2 CS plus 1 times LS is equal to that. And now basically we can flip it. So we can get E out over E in. Oh, sorry, I in. So I've got this over here, E out. I divide both sides by I in. I'm left with an R2 up top and an R2 CS plus 1 down here. That's on my right-hand side. Now I can take this and divide both sides. So actually what's happened is that this denominator is going to come over here, and really that's going to cancel out this part. We get R2 CS plus 1 times LS. So that comes over there, and then we've got the R1, R2 CS plus R1 plus R2 plus R2 CS plus 1 times LS. We have some cancellations. This cancels out. I can't cancel out the R2. I can't cancel out the LS. And so now we're at our final part, which I'll write right here. E out over I in equals R2 LS over. I want to start with the highest order first. So I'm going to start, this is an it's an S squared, so it's R2 CLS squared. I have an LS, and I have an R1, R2, C. And then lastly, we have an R1, R2. The final answer looks pretty nice. It's a second order transfer function. It's got all the components. It took some algebra to get there. So we've got the same, either method you want. And I don't know if the other method wanted to go through KVL, KCL, that might have been faster. Again, like I said, it could have been, depending on your skill with this. The real wrench in the system was that R1 right there. It really made it difficult. Now, and there's other ways that you could probably look at the problem, depending on your experience with impedance, but we should be able to get to a second order equation. Yeah, you had a question? Yeah. Well, that was, you can break this denominator into R2CS plus 1 times LS. So that's where you get the S squared. Yeah. So, yeah, kind of complicated. Now, I know you had some trouble with this. This was pretty hard. It's a difficult problem, trying to solve E out over I in. The test, it might not be as hard, but you won't have me. So the main point is making sure you write down all your definitions, try to make sure everything's mapped out, and then I know that the algebra can be hard, but just taking it one step at a time. I'm going to plug this in here. I'm going to try to see what cancels and so forth. Yeah. Yeah, the algebra is like, once you have those equations and you set them up, the algebra is the same either way. It's going to be somewhat difficult. You got to keep track of things. Like you can have 3 different equations and then plug them in, and again, you're just trying to solve for the same kind of. Okay. Let's see. I'm gonna post these slides. If you have any other homework questions, you can stick around. I just have some problems up here. I put some comments on the homework, so you can definitely read there. As for test prep, I would go through, try some problems from the slides. Maybe even redo homework problems. Anything like that can be helpful. Really, anything in class or on the homework is good test prep. So if you got questions, you can stick around. We can go through some problems. Otherwise, you can take off. Doing okay. Yeah. Yeah. It's not. Yeah. Well, what's the heat coming out? Cold. Heat goes from cold to hot.
Hot to cold when it's going to go from like the ambient, which is harder than the actual. So after that, I guess to equalize, this is going to be faster.
Yeah, there's only one heat flow.
So because it's cold, it should only have one heat flow.
Yeah, it's always going to go from top.
You're right.
So it's going from outside to.
Okay, so in that case, my ins and outs should be more like the heat of the ambient temperature.
The output is the temperature. Yeah, that's what we're trying.
I see. Okay.
As a function.
Should I have my input as like the temperature of the ambient, or should I just keep it as like the heat?
You could. Yeah, you could, or just keep it as heat. That's fine.
Okay. Okay. In that case, that would change over here as well. So when meeting heat coming out,
Right. So this equation, you don't have a Q out, you just have this.
yeah. Sure. So this
Because the other confusing thing was how you went from a Q to a T. That's a very different thing. So,
I forget. Just do something with these. In that case,
but yeah,
for the-
but this definition just goes in here, and then yeah, you can move all the T's to one side. So you get something similar. It's just it should be a 1.
okay. So for the heat of the ambient, can it be like the temperature? I mean, over the resistance, or does it have to be something like this, right? Like for example, is this correct right here, or is this correct right here? Or for QA,
This is not correct.
that is not correct.
But these are
If because the temperature of the ambient is greater than the temperature
yes.
of the inside, that's why I have to
That's
put
why
T
T
of
is
minus.
minus.
Yeah. Okay.
And so when you plug that into there, then you should be able to move T's to the side and get to a similar transfer.
Okay. So in that case, I go with this equation right here, and that's how I get the actual frequency.
Yeah.
Okay. That makes more sense.
So you plug that in. Yeah.
Okay.
I'm gonna stop my.